This is the 8.4 Using Exponential Functions lecture. So now we're going to be doing a bit more work on using exponentially functions. All right. First, we're going to look at these and remember what we learned last class. So, 4 to the x. Well, since the 4 is greater than 1, we know it is growth. The only one showing exponential growth is C. Okay, I think the below is the answers, A, B, C. All right, -4 means it is rotated around the x-axis, so that's going to be A. And the 1/4 means it is decay, which is B. Okay, so that's basically some of the stuff we went over last class. All right, if 2 points of an exponential function of the form a equals ab to the x are known, the function rule can be determined. Okay, just like with linear equations, if I have 2 equations and 2 variables, I can figure out the answer. And that's what we have here. I can figure out an equation for it. Okay. So, example 1, write the exponential function whose graph passes through, here's 2 points. Okay, so we have x and we have y. So we plug that into this form. Y is 12, so I have 12. Here, let's highlight these. It makes it a little easier. Okay, so y is 12, so I have 12, equals ab to the x. X is 2, so it's a 2. And then our second equation, y is 96, and x is 5, okay? So what we do is we solve one equation for the variable a. We do that by dividing both sides by b squared. We end up with a is equal to 12 over b squared. We then plug that into the second equation for a, and that's what we've got here, 12 over b squared times b to the 5th. Well, I know that b to the 5th divided by b squared is b cubed. Okay, so that's what this is. B to the 5th over b squared is equal to b to the 5 minus 3, 2, which is b to the 3rd. Okay. So I end up with 12b to the 3rd is equal to 96. So now I divide both sides by 12. I have 8 equals b cubed. If 8 is b cubed, I know that b has to be 2. All right, now I plug that, change colors. I'm going to plug the 2 into this equation, right? And there it is. A equals 12 over 2 squared, which is 4, so that gives me A is 3. So I have A and I have B. And there we go. So using 2 equations, we can solve this. All right, functions of the form f of x equals a times 1 plus r to the x can be modeled both, can model both the exponential growth and decay, just depending on what r is. This is of an initial amount a and a constant percent of change r in a time period of x. The base of the exponent, b, is equal to 1 plus r. This is the growth factor. Okay. So let's look at this. Exponential function. y is equal to a times b to the x, or y equals a times 1 plus r to the x, because b is equal to the 1 plus r. This is our new base. That's how we find the base. Because what we're talking about is growth and decay. We start with an original amount of 100, that's like 100%. Okay, so it's 1. And then a percentage of growth or decay, which is r. All right, so you can see here we have our equation. Beginning with a population of approximately 2 million people, Nevada was the fastest growing state from 2000 to 2010. Okay, so what does this tell us? This is telling us that T equals 10. The 2 million is our starting amount. So that's our A. All right. With an average annual increase of 3.2%, this is giving us an R of 0.032. Okay, write an exponential function modeling Nevada's population growth in millions. That's why we use, let's go back, hang on. Okay. This is why we use 2 instead of 2 million, because it's in millions. All right, so write an exponential function modeling Nevada's population growth. All I'm going to do is plug the values I now have into here. I use a 2 for my 2 million. I use a 1 plus 0.032 because that's my R. And to the T in this case, T is 10 years. So I plug this all in, and I get approximately 2.7 million. So this is the Nevada's 2010 population, 10 years later. Whoa, apologies. All right, now finally, this is all based off that same problem we just did. Determine the average annual percent increase during the 90s if Nevada's 1990 population was 1.2. Okay, so we start out at, here's my initial population of 1.2. It grew to 10 in the year 2 million in the year 2000, 10 years later. And what we're doing is trying to figure out R. So the first thing I'm going to do is divide both sides by this 1.2. That's what you see right here. Okay? And then I have to take, because of this 10th, I have to take the 10th root. The 10th root is right here. That's equal to my 1 plus R. Now I subtract 1 from both sides. And that makes those cross out. I've got R is equal to the 10th root of 2 over 1.2 minus 1. Plug this all into my calculator. I get 0.052, so it's approximately 5.2%. So this is what R is equal to, approximately. All right, after Nevada's silver rush, its population fell from 60,000 in 1880 to 47,000 in 1890. Again, a gap of 10 years. Okay, so that's where I get this 10 right here. All right, my initial amount was 60,000. My second amount is 47,000. And now I solve for R. All right, I divide by the 60,000. And this is going to give me 47,000 over 60,000. So it ends up 47 over 60 because all those zeros are all crossed off. So I have 47 over 60 here, and then I take it to the 1/10 in order to pull that off. All right, so these cancel, and I now have that to the 1/10. So I put this in my calculator. I subtract, and I get this. I subtract 1, and R has a negative growth or a decay of 2.4%. Basically the 0.024. All right, assuming the population continued to decrease at the same rate, estimate Nevada's population in 1900. Well, we now have our R. This is 1 minus okay, so that's giving me the 0.976. I plug that in. I'm doing it off the original amount of 60,000. I'm decaying at that rate over a period of 20 years. Okay, so that's what they want to know is after 20 years from the original 1880 data. Well, it will now be approximately only 37,000 people in 1900. All right, the half-life, now this is another kind of problem we get is this half-life decay, which are kind of weird. The half-life, H, of an element is the time that it takes for half of the radioactive isotope to decay into a stable isotope of another element. So, function of T, this is based on the amount of time. I have my original amount of radioactive element, and it's the 1/2 half-life, 1/2. So this becomes, because it is the half-life, and then it is the length of time divided by the element's half-life. Every element has its own half-life. So you have to be given that value or given everything else in order to find that value. All right, so this is the basic equation we're going to be using. All right, so the half-life of carbon-14 has been determined to be 500, let me put this in highlighting, 5,730. That's why this becomes 5,730. A piece of wood believed to be 4,000 years old, okay, that's your T, is 4,000, so it's been around for 4,000 years, now contains 19 grams. Okay, I can use yellow. 19 grams, that's my 19. Predict the original amount of carbon-14. So what we're looking for is the original amount, which is A. All right, so we plug everything in. First we're solving for A. Plug everything in and solve for A. So to solve for A, I divide by all of this. So that's why you see this has now come down to be in the denominator under the 19. So A is equal to 19 over 1/2 to the 4,000 divided by 5,730. We plug this into our calculator, and we get what the original amount is. Predict the amount of carbon-14 in the wood 100 years from now. Okay, so we have another 100 years. And it's saying it now contains 19. So that is now my A. For right now, that's my A. Okay, so that's my A is the 19. It comes from that 19 grams because it says now contains. All right, and they want to know, okay, notice I'm using the same half-life because we know that's the half-life. But the time has changed. It's now 100 years from now, so I use 100. Plug this into my calculator, and out comes 18.8 grams. So my answer to A was 30.8 grams, and B is 18.8 grams. And now you've got your homework. Okay, thank you for listening.